Hi, in this video, I'm going to go through the OCR AS-level chemistry paper. This is the 2020 paper, and this is the second half of this paper, paper one, AS paper one. Second half of this, I did the first half in an earlier video. Okay, so the first question is about bromine. Bromine reacts with phosphorus, P4, to form PBr3, complete the electronic configuration of a bromine atom. Okay, so we can see, look, we've got hydrogen, helium, it's 1s, lithium, beryllium, so that's going to be 2s, 2 in there, and then we've got 6 electrons in 2p, that's all full up. Next, we're going to have 3s, that's full up, so 3s2, 3p, that's also filled, 3p6. Then we go to 4s. Okay, so we've got 4s, 2 in there. The d orbital, 3d, that's completely filled up. All 10 there, so that's 3d10. And then we've got 4p. Okay, and how many have we got in there? We've got 1, 2, 3, 4, 5. 4p5. That's the answer there. Equation for the reaction of phosphorus with bromine. So we're going to get P4 plus Br2, and it's going to react to form PBr3. So we need to balance that by putting a 4 there. That means we need 12 bromine atoms. So that means we need to put a 6 in front of our Br2. Okay, right. The compound of bromine is a solid at room temperature. Okay, so we can see when it is a solid, it won't conduct. When it's a liquid, it will conduct. Okay, so that is obviously an ionic compound. So it's an ionic lattice. Why the difference in electrical conductivities? Well, electric current is the flow of charged particles. Normally that's electrons, but it's not in this case, is it? It's an ionic solid. It is ions. And why can't it conduct when it is a solid? Well, because the ions are not free to move in the solid. The ions not free to move, they're in an ionic lattice. In a lattice. When you melt it, they are free to move, so it will conduct. Okay, bromine reacts with fluorine to form compound A. Okay, compound A is a liquid room temperature, but you can easily vaporize it. Okay, and we're going to use the ideal gas equation to determine the molar mass of this. Okay, the molar mass, let's call that the MR, and so the molecular formula of compound A. Right. So what do we need? We need the ideal gas equation. We need PV is equal to nRT. We want to find out the number of moles we've got here. Well, we're going to do that. And of course, we know that moles is equal to mass. That's N for moles over MR. So rearrange that. We're going to get MR is equal to the mass over the number of moles. We can work out the MR. But first of all, we need to work out N using the ideal gas equation. So we're going to rearrange that. So we get N is equal to PV over RT. Now, when you use the ideal gas equation, you've got to be really careful about units. Right, so pressure is measured in pascals, so there's no problem there because they're giving it in pascals. So you've got 1 times 10 to the 5. The volume, you have to be really careful. We've got 76 centimeters cubed, but that's got to be measured in meters cubed. Okay, there are 1,000,000 centimeters cubed in a meter cubed. And usually we measure volume in meters cubed, though we nearly always use dm cubed, don't we, or centimeters cubed. So that's going to be 76 divided by 1,000,000 by 10 to the 6. Okay, and that is going to be the ideal gas constant is 8.31. And the temperature, well, we have to convert the temperature again, because be careful with the units. 100 degrees C, add 273, that's 373 Kelvin. It's got to be in kelvins. Right, put the numbers into that, and we get 2.452 times 10 to the minus 3 moles. Now we can put that value of the number of moles into our equation there. Let's do that. We're going to get, so the MR is equal to the mass, 0.428 grams, divided by the number of moles, and that gives us 174.6. That's the molar mass. Okay, and you can't really go wrong there unless you mess your units up, really. I think that is what you've got to be careful of in the ideal gas equation. Right. So now we've got to then suggest a molecular formula for compound A. Right. So we've got this value of 174.6. We know that bromine has that's 79.9, and fluorine, well, that's got an atomic mass of 19. So, right, let's say we have one bromine, right? Let's presume we've got one bromine. Bromine can have you can form 5 bonds, so it can form 3 bonds quite often. So we've got some ideas what it might be. Right, let's say so we do 174.6 minus 79.9. That gives us, so that's the mass of the bromine there. That's going to give us there's a bit of trial and error involved in this, really. 174.6 minus 79.9, that gives us 94.7. Now let's see if you can do that divisible by 19. So it's just made up of fluorine. So let's do 94.7 divided by 19. That gives us 4.98. Okay, so yeah, it's going to be 5. So I think we're pretty sure that that is BRF5. And if you just want to make sure that's right, like, so let's say we had 2 bromines in there, right? So that's going to be 2 times 79.9. That's 159. So that's it's not going to work. That is the answer, yeah. But there is a little bit of trial and error there, and you've just got to be patient if you don't get it right the first time. Okay. Next question. Question is about barium hydroxide. 3 marks. Barium hydroxide is an alkali which releases hydroxide ions in aqueous solution. A solution contains 3.89 of barium hydroxide, 3.8 grams in 100 centimeters cubed. Calculate the concentration of hydroxide ions in moles per decimeter cubed. Okay, so first of all, let's work out our moles of barium hydroxide. And we have to bear in mind later that's going to give each 1 mole of barium hydroxide gives 2 moles of hydroxide ions in solution. So that's going to do the mass over MR for that, the molar mass. Our mass is 3.89. Now the MR of barium hydroxide is 171.3 if you work it out. Okay. So that's over 171.3. That gives us 0.0227 moles. Okay. So how many moles of OH minus is that going to give us? Well, we can see here, look, we've got 2 hydroxides for each mole of barium hydroxide there. So right, moles of OH minus, 2 times 0.0227. That gives us 0.0454 moles. Now we need to work out the concentration. So of course, concentration is equal to moles over volume. Concentration of hydroxide ion. We've got 0.0454 moles of hydroxide ions. And here we've got 100, the volume is 100 centimeters cubed. That's 0.1 dm cubed. So that gives us 0.454 moles per decimeter cubed. That is our answer, and that's the 3 significant figures, as it says, as it asks us in the question there, yeah? Okay. Right, so as a student carried out a titration to determine the concentration of an aqueous solution of barium hydroxide. Right, okay, so what we're going to do is let's draw a little picture. We're going to have a burette. And in the burette, we're going to put nitric acid, HNO3. And the concentration is 0.16 mole per decimeter cubed of that. It tells us in the question there. And we don't know the volume of that just yet, but we're going to get that later, presumably. That's going to go into our conical flask. And in the conical flask, we have 25 centimeters cubed of barium hydroxide solution. And we don't know the do we know the we don't know the concentration of that's what we're going to have to find out. So the concentration question mark. Oh, the mean titer is 26. That's 26.75 centimeters cubed. Now, but we're going to convert that volume into dm cubed in the equation. So let's do that now. We divide by 1,000, 0.02675 dm cubed. Okay, this question here is what is meant by, they keep doing it till you get concordant titers. What does we mean by concordant titers? Well, it's titers which agree with each other to within, so they are within the usual stipulation is they're within 0.1 centimeter cubed of each other. Okay, so now we've got a question part 2 here. And we've got to calculate the concentration of the barium hydroxide solution. Okay, now we have got the equation there. We need that, and look, this is quite important. That we've got like 1 mole of barium hydroxide requires 2 moles of nitric acid. Now, as always in titrations, we're going to use this equation. We're going to use concentration is equal to the moles over the volume in dm cubed. Now, to be able to work things out with this equation, we need 2 things, and we can work out the 3rd thing, can't we? So with the barium hydroxide, well, we can't do anything there because look, we know the volume of the barium hydroxide, but we don't know the concentration, so we can't. That's not the starting point. The starting point is, look, we know the concentration of nitric acid and the volume of it, so we can work out the moles of nitric acid. Let's do that. Moles HNO3 is equal to the concentration times by the volume is equal to 0.16 multiplied by the volume in dm cubed, 0.2675. That gives us 4.28 times 10 to the minus 3 moles of nitric acid. Now, look, 1 mole of barium needs 2 moles of barium hydroxide, needs 2 moles of nitric acid. So what's the moles of barium hydroxide we've got? Let's do that. That's equal to a half. We need half the moles of that, 4.28 times 10 to the minus 3. That gives us 2.14 times 10 to the minus 3. We need to work out the concentration of it right now. Look, we know the number of moles, we've got the moles, and we know the volume. The volume is 25.25 centimeters cubed. So let's do that finally. So we've got concentration, moles over volume. Moles, 2.14 times 10 to the minus 3. And the volume is 25 centimeters cubed. That's 0.025. And that is going to be equal to 0.0856 moles per decimeter cubed. That's the 3 significant figures. We should give it to 3 significant figures because our least accurate piece of data here is 3 sig figs. So that's what we should do. Okay, that is that one done. Okay, a student plans to prepare a solution of barium hydroxide from barium by 2 different reaction routes. Outline 2 reaction routes for barium hydroxide. So, how can we make barium hydroxide? Well, you should know that all the group 2 elements, except for magnesium, forget about beryllium, they react with cold water in the following way to make the hydroxide. So, we're going to get barium metal and add it to water. We get barium hydroxide solution made. And we get hydrogen gas liberated, okay? So we need to balance that. All we need to do is put a 2 there, okay? So what you're going to say there is you're going to place some barium in an excess of cold water. That'll do it. Right. The other way of doing it is, well, you can, first of all, so method 1, you can react barium oxide with water. Barium oxide will react with water, as all of the group 2 oxides will react with water to an extent. Magnesium oxide, not that much, because the product is very insoluble. Barium oxide reacts with water to form barium hydroxide. And that is balanced, don't need to do anything there. But of course, how do we get barium oxide? Well, we need to burn some barium in oxygen, which is in air. That will give you barium oxide. And then you dissolve the barium oxide in water. Well, better give the relevant equation for forming barium oxide, I suppose, which is fairly straightforward, but it's just going to be Ba plus O2 equals to formula of barium oxide. Of course, it's group 2, so it's a 2 plus ion. Oxide is a 2 minus barium that, and so to balance that, we need half O2. Okay, so this is a question about making ammonia, and it's going to be Hess's law. Ammonia is manufactured by reacting nitrogen and hydrogen, shown in that equation, and they give us standard enthalpy changes of combustion. So we've got to calculate the standard enthalpy change of formation. Now, this is a little bit confusing here. Right, so because we're kind of mixing up the formation and the combustion thing. Right, let's write the equation for the formation of NH3. Now we have to be careful there, because what is delta HF? It is, the definition of it is to form the enthalpy change to form 1 mole of substance, okay, in standard states, etc., etc. Now, so it's not this equation here, because look, we're forming 2 moles of ammonia there, and that's, so you have to be careful. You have to halve that. So what we want to do is we want to find out the enthalpy change for this. We want a half N2 plus 3 over 2 H2 is going to form 1 NH3. Okay. Now we're given combustion. Okay, delta H combustion. So what you should do is, if you're given that data and you want to work, we want to work out delta H there, which I'll put in red. That's delta H. That is delta H formation, isn't it? Well, we want the combustion products as defined as this. So we want combustion products down here. Okay, so the combustion products are going to be hydrogen, hydrogen oxide, water, and an oxide of nitrogen. Okay, so we're not going to worry about which oxide of nitrogen because they don't really need to know. But now, which way should the arrows go? So we're going to have one arrow. Sorry, I'm going to have one in blue, and I'm going to do one in red. Okay, now, which way am I going to put the arrow on those? Well, we are burning these things and turning it into combustion products. So the arrows should both be going down. And that one's going down. Now, okay, let's look at the blue arrow. What we're doing there, we are combusting half a mole of nitrogen. So that is plus 180. So that's going to be a half times plus 180. And we are burning 3/2 moles of hydrogen. So it's 3/2 times that. That's a minus number, 286. Right, let's add that up on the calculator. What do we get? We get minus 339. That comes to. Be careful there because you've got a plus there and a minus in the other one, haven't you? And when we combust ammonia, that they tell us is minus 293 there, in red. Just got one mole of that, so it's minus 293. So what is our delta HF equal to? So delta HF is equal to, right, we are following the blue arrow, aren't we? Okay, so we don't mess about with the sign there. So that's minus 339. But this one, we are going against this red arrow, going against it. So we have to change that into a plus. So that's going to be plus in red, plus 293. And that is equal to minus 46 kilojoules per mole. And delta, okay, that is our answer there. So a little bit tricky, that question, because they're trying to confuse you into drawing, I think maybe the energy, the Hess's law cycle that you'd normally draw with when you give them delta HF values, but we need to use the combustion one there. Okay. The industrial manufacture of ammonia is carried out at an increased temperature and in the presence of a catalyst. Explain using Boltzmann's distributions why increasing the temperature and using a catalyst both increase the reaction rate. Okay, so let's draw, I'm going to draw one Boltzmann distribution here. Okay, so the Boltzmann distribution we put on the y-axis, we put, that's the number of molecules. And on the x-axis, we're going to have the energy. Right, now the Boltzmann distribution always starts off, so 0 molecules have 0 energy. So that starts off at the origin, and you'll get a curve something like that. It's like skewed, isn't it? Okay. Right, that is at temperature 1. Now let's do what happens at a higher temperature. At a higher temperature, your Boltzmann curve, right? So this is the low temperature. This is going to be the most probable energy, isn't it? Now the most, it's not actually the mean because it's not symmetrical, but it's the most probable energy of a particle. If you increase the temperature, the most probable thing is going to be higher. So this whole curve is going to shift to the right. But we've got to be careful that the area under the curve stays the same, because that's the total the area under the curve is the total number of molecules, which is going to stay the same. So we need to draw something like that. Okay. So the area under those two curves is the same, but you can see the most probable energy at the higher temperature is like that. So yeah, the curve should be to the right, but the peak should be lower to ensure that the area under the curve is the same for the both. Right, so the red is the higher temperature. Right, now let's say that the activation energy for the reaction is there, EA. And we would say, right, so at low temperature, which molecules have sufficient energy? Well, it's these ones, which are shaded in green. At the higher temperature, which molecules have it? Well, it's the green bit and also this extra yellow bit here. So you can see a higher temperature, a higher proportion of molecules have a greater energy than the activation energy. Let's write that down. Have energy greater than the activation energy. So the rate of reaction. So the more of the collisions are going to be effective. Now we need to talk about the catalysts. Okay, so it's easiest to draw the diagram for that one. So I'll draw another Boltzmann curve for the catalyst. That in black. So once again, we want the number of molecules, and we want the energy of the molecules there. So at one temperature, you're going to have a Boltzmann distribution like that. Let's say that the activation energy here is normally there. But if you use a catalyst, what the catalysts do, they lower the activation energy. So let's say it's there. So you can see the proportion of molecules which have enough energy to react are the ones with greater than the activation energy, only a small proportion there. If you use a catalyst, because you lowered it, you get that yellow area plus the green area. All those molecules can react. So the rate of reaction is faster. That's EA with the catalyst. Okay. Right, a bit of organic chemistry now. Unsaturated hydrocarbons. Two reactions of propene are shown below. In the boxes show the structures of the organic products. Right. Polymerization, then this one here, what happens in polymerization? Well, if I just draw one next to it, what happens is we break the double bond, don't we? Break the double bonds, and we form a new bond between those two, and this sort of carries on forever. So if I do one repeat unit, you can see what we're going to have is we're going to have two carbons. That carbon's got a hydrogen and a hydrogen. The other one's got a methyl and a hydrogen on it. Okay, and that's going to be joined onto the next carbon in the next repeat unit. So I should put a bracket around that. That's one repeat unit. Okay, next, if we add HBr, right, so you're going to have an addition reaction there. You're going to break the double bond, and you are going to stick on. So in the HBr, the H is going to stick to one carbon, and the Br is going to stick to the other one. But of course, that's asymmetric. So you've got two products because they could go the other way around, couldn't they? So let's draw what they look like. So we're going to have here, right, the double bond's gone. We've got the original hydrogen, the original methyl, and the original hydrogen. And here we stuck on a new hydrogen and the bromine on that one. And in the other diagram, I'm just going to swap the positions of those two things. So that's simply going to be the Br there. And those two things are different. Those molecules are not the same, are they? One is 2-bromopropane. That's this one here, 2-bromopropane. and the other one is 1-bromopropane. And you will get, you probably remember, you get more of the 2-bromo, if you remember. That's a major product. Okay, propene also reacts with bromine. Okay, outline the mechanism for this reaction. Show curly arrows, dipoles, and products, usual. Okay, so what happens is, right, we've got a Br2 molecule, which doesn't have a dipole because obviously both bromines have got the same electronegativity, but you get an induced dipole, you remember, because all that negative charge in this double bond there means that you are going to get that will become delta positive, partial positive charge, and the electrons will go down the other end of the molecule, give that one there. Okay, so the first step in the mechanism is for the pi bond to break. The pi electrons will move onto the bromine. That bromine, then the bond between the 2 bromines will break. So do that. So if you draw the product, well, we're going to have a bromine stuck to this carbon now. And nothing's much happened to this one. Right. And so this bromine has now formed Br minus. Okay, and this doesn't look right, does it? Because that carbon is only forming 3 bonds instead of 4. Also, if you look at the left-hand side, we've got no charge. There's no charge. But on the right-hand side, we've got a negative charge. So that means there must be a positive charge somewhere on that thing. And where's the positive charge? It's on that carbon. It's there. It's called a carbocation. All right. And why is that a positive charge on that carbon? And what you can think about it is because, look, there's a pair of electrons in that pi bond, and this carbon, owned one of those electrons, but they've been given away to the bromine now, so it's short of an electron. It's positive. All right, and obviously this negative ion is now going to react with the carbocation, so we need to draw a lone pair, which are the movement of the electrons goes from that onto the carbon. Finally, we need to draw the product. So we've got 2 new bromine atoms, double bonds gone. We've got a bromine atom on each carbon. It's an electrophilic addition reaction. There's our product. Okay, the alkynes is an homologous series of hydrocarbons. Okay, table shows 3 alkynes there. Okay, so you've got a carbon-carbon triple bond there. Right, and okay, explain what is meant by the term homologous series. Okay, so OCR pretty keen on this, and I wouldn't necessarily say it, but if you look in the mark scheme, it always says this. I would say for homologous series, I'd say the same functional group. And I would say similar chemical properties. OCR pretty clean on you saying this, so I would always say it. Okay. I would also say actually same general formula, but they don't really like that at OCR. I.e., I'll say CnH2n plus 2 for an alkane. Yeah. Well, these aren't alkanes, but they don't like that. What they want you to say is the formula differs between 2 members by a CH2 group. That's what they like you to say. Okay, so I would say it. Right, suggest the general formula of the alkynes. So to help us, I've just copied in that little bit there. Okay, so I'm going to say, look, it's Cn Right, for this one, you've got 2 carbons and you've got 2 hydrogens, okay? But it's that, you might think it's CnHHn, but it's not, because this is different here. So I think what you've got to say is Cn H2n minus 2. That works, doesn't it? If you look at that. And if you think about what's the formula of the alkanes with no double bonds, that's CnH2n plus 2. The alkenes, where you've got 1 double bond, is CnH2n. So we've lost those 2. So when you've got a triple bond, the alkynes, you lose another 2 hydrogens. So it's CnH2n minus 2. Okay, I think this is the last question. Propyne reacts with bromine to form a saturated compound. Write an equation showing the structure of the organic product. Okay, so propyne is going to be, okay, propyne, you've got 3 carbons there. And between 2 of them, you've got a triple bond. So that's going to be CH there. That carbon has got no hydrogens on it, and this one has got 3. Right, you're going to react that with bromine. So you're going to break that triple bond. So let's call that carbon number 2 and number 3. Okay, so the N one's not going to change. Obviously, that's not going to, nothing happened there. Right, that carbon you're going to lose the double bond, triple bond. Sorry. So that means you're going to need 2 bromines on there. So it's still got 4 bonds. And for carbon number 3, again, you're going to have 2 bromines on there. So it's got the right number of bonds, 4, and you've got a hydrogen there. Okay, so how many bromines do we need to balance that? We're going to need 4 bromine atoms, so that's 2 bromine molecules. There is our equation. And that is the last question on the paper.